In our previous lessons, we were looking at intermolecular forces, and now we'll be looking at practical investigation on melting and boiling points of similar sized molecules. This will give us to show us really what we learnt in everyday life. The aim of today will be to use second-hand data to plot the melting and boiling points of similar sized molecules. And we'll do this by plotting separate graphs of melting and boiling point versus molecular weight for each set. And this will give us an indication of, whether the molecular substance will be asymmetrical and symmetrical, and what kind of bonding is involved, and therefore tell us really what's happening, why we're getting different sets of melting points and boiling points. We'll then identify the graphs for each set, which molecules exhibit hydrogen bonding, dipole-dipole forces, or neither, like dispersion forces. So in the first set, we will be looking at NH3, CH4, neon, and water. And the molecular weights are here. And we'll be plotting the melting points against the molecular weight, as well as the boiling points against the molecular weight. So when we do this, we'll get a graph like this. So note the axis here are the different molecules, and they're increasing in weight. And then we're looking at the temperatures of both the boiling point, yellow line, and the melting point, blue line. Ammonia, hydrogen fluoride, and water have higher boiling points and melting points, so we write BP for boiling point, MP for melting point, because of existence of strong intermolecular forces such as a hydrogen bond. That's why these ones here are quite high compared to these ones here. Methane and neon have lower melting points and boiling points because they only really have weak intermolecular forces, and these are dispersion forces. So dispersion forces are weaker, letting them have low melting points and boiling points, because we don't need to put much energy into it to break them apart really. So in another set of data, we'll be looking at HF, so hydrogen fluoride, hydrogen chloride, hydrogen bromide, hydrogen iodide. As we go down, we increase in weight, and we'll be plotting the melting and boiling points again. And when we do this, we'll get a graph like that. So similarly, boiling point in yellow, melting point in blue. We get hydrogen fluoride to hydrogen iodide. So the melting point and the boiling points increase as we increase molecular weight. As we go from hydrogen fluoride to hydrogen iodide, we're going down a group. And down the group means increase in weight, and we get an increase in weight here, increase in boiling point and melting point. So HCl, hydrogen bromide, and hydrogen iodide are increasing in weight, and we're getting more and more temperature. Hydrogen fluoride, however, doesn't fit this trend. It's the smallest, but it has the strongest intermolecular forces between it, and therefore we get high melting and boiling points. So we need to put lots more heat in to break them apart to change the state than compared to these ones here. Hydrogen fluoride can form hydrogen bonds that result in unusually high melting and boiling points because they're stronger, therefore we have to put more energy to break it up. So when we're looking at trends, usually as we increase the weight, we'll get an increase in melting and boiling point because more electrons are involved, therefore we can get more bonding, intermolecular bonding. But sometimes we have something that's slightly different. So in this case it was HF. HF, because it has hydrogen bonds, it has stronger bonds between the molecules, and we need to put more energy in to break them apart compared to these. So that's a difference in the trend. So we need to really look at the different types of intermolecular forces to determine why we get trends and why we don't follow trends as well. So using that, we can answer just a few simple questions. So question 5, identify a trend common to the graphs here. So as we increase in period number, that means we're increasing in weight. What are we really seeing with the melting and boiling points? So generally what we see is that the boiling points of hydrides increases as you move down a group, so increasing the period number. So we see that here with the methane, we're going up to higher temperatures as we increase in the period number. Period number means increase in mass. And we also see that here from the HCl up to the hydrogen iodide. But we don't see that with water and hydrogen fluoride because of hydrogen bonding being present. So next, question 6. Identify 2 hydrides whose boiling points don't fit this trend. These ones all fit the trend because they're all kind of in a straight line. But this one, the straight line is here up to the HCl, and then we have a little bump here. So the 2 that are not in this trend are really water and hydrogen fluoride because they're higher than expected. If it was with the trend, we'll expect them to be somewhere down here, but they're not. They're all the way up here. So question 7, the boiling point in these covalent compounds is determined by intermolecular forces. Identify the intermolecular forces present in water and hydrogen fluoride that are not present in any of the other hydrides. So we need to make sure we identify what's different between water and hydrogen fluoride and the rest of them. So we know that water is a bent molecule. Bent molecules are polar, and also it's has lone pairs on the oxygen, so it's going to have hydrogen bonding. So hydrogen bonds are involved in this, and that's why we're getting a higher boiling and melting point. So in summary, remember that trends usually is that if we increase in the weight, we're going to have an increase in melting point and boiling point, but sometimes things don't follow the trend like water does and hydrogen fluoride doesn't, So these are because there's hydrogen bonds present, and hydrogen bonds are more strong, and that means we need to put more energy in, so more heat in, to change state.